Okay, there we go. Seems to be a little bit of glare. That helps. Some. Could just be my angle. It looks better when I'm down here. Okay, we're recording. All right. The way I used to have this course set up, it was in 4 units, and we had 4 exams. And I soon found out that was a little much. So I've been splitting it up. But the slides kind of are a holdover. And this item here is not part of the course content outline. So that's why it's there, but it's not there. We don't cover that one in the class. I just found it easier just to leave it there and just not do it. But we're going to look at redox reactions. And the first thing we should do is define our terms. What is an oxidation reduction reaction? And we say redox reaction just because it flows better. But these types of reactions are those that involve the transfer of electrons. Electrons, and this is a prime example, where we take sodium metal and react it with chlorine gas. And when you do that, by the way, it's a very violent reaction. But the electrons are transferred from sodium to the chlorine. And that's why the sodium chloride, or table salt, ends up with sodium ions +1 charge and chlorine ions -1 charge, because we've transferred electrons. And the electrons just naturally want to be with chlorine, and they'd rather not be with sodium, and primarily because if we look at the periodic table, the chlorines want to look like noble gas. And if they gain an electron, they look like argon. They're not argon, but electronically they look like argon. And then sodium wants to look like neon. So it loses an electron, and that makes it look like neon. So that's one of the driving forces for these reactions. When you transfer electrons, or you remove or add electrons to an atom that's in its neutral elemental state, it's tending toward a noble gas configuration. It just wants to look. So we transfer an electron from sodium to chlorine, and everybody's happy. Okay, so that's a redox reaction, anytime we transfer electrons. Now, there are terms that we need to agree upon. Oxidation. Oxidation is loss of electrons. Anything that loses electrons is said to have been oxidized. And reduction is gain of electrons. So anything that gains electrons is said to have been reduced. In this case, sodium has been oxidized and chlorine has been reduced. And we use this mnemonic to, sometimes it helps. Oil rig. Oxidation is loss, reduction is gain. So you can fall back on that if if it ever starts spinning in your head, and put the brakes on and say, that's what it has to be. Okay. So let's take this reaction as an example. And we have 10 2+ ions reacting with iron 3+ ions, and the products are 10 4+ ions and iron 2+ ions. Now, of course, you know from earlier in the semester, these charges don't balance, right? So there must be some counter ions in there to balance them. This probably comes in as tin chloride, and even iron chloride would be a good way to get them in a solution together, right? We just leave the chlorines out because they're spectators, right? Remember when we wrote complete ionic equations and then we knocked out the spectators and we had something left over? This is the same idea. So we're only interested in these parts of the equation. So if 10 2+ goes to 10 4+, have we added electrons or subtracted electrons? What if we add an electron to a 2+? What does that do to it? It goes from 2+ to 1+, doesn't it? All right? Let's do it this way. Once you get over this hurdle, ways of thinking of how electrons move, I think everything will fall into place. Okay, so if we go from this 10 to that 10, we're going from 2+ to 4+. Think of it as a math problem. You're starting with 2+. Let's just say you're starting with 2. And you're going to add something to it. And you end up with 4. How can you add something to 2 and end up with 4? Mm-hmm. -2. That doesn't work, does it? That makes it 0. Okay, so my math analogy doesn't work. Let's try it a different way. We have 2 protons. How about that? Because all positive charges are due to protons. And then if we end up over here with 4 protons, and this is, no, that's not right. It's the charge. If you start off with 2 positive charges and you end up with 4 positive charges, well, let's take 10. Let's just do 10 by itself. It's 50. Right? 50. Okay. This 10 has 50 protons. And it has 50 electrons to start with. Right? So it's neutral. If we end up with an ion that's 2+, how do we get 2+ out of this arrangement? We have to have fewer electrons, don't we? We can't change the protons. If we change the protons, we got a different element. So we can only mess with the electrons. So in that case, we need 48 electrons, and 50 protons would give us a 2+ charge. So on this side, we still have 50 protons, but we want 4+ charge. So that means we need 46 electrons. So in order to get from here to here, we've lost 2 electrons. Okay. I'm bound and determined to get there one way or another. So this is a loss 2 electrons per 10. And since we only have 1 10, the total is 2 electrons. Okay. Now we use similar reasoning to go from this iron to that iron. And to go from 3 plus, 2 plus, we have to gain 1 electron per iron. Okay? But we have 2 irons. 2 electrons. Okay? And when the equation is balanced, this always has to equal that. Whenever you have an oxidation, you always have a reduction, and they have to balance. Okay. So the 10-2 has been oxidized. Right? Oxidation is loss. And the iron has been, let's see, this is oxidation. This is reduction. Okay. This procedure, now in this case, these are ions. So these are actual values for each of these species. But when we start assigning oxidation states, as we call it, to other elements in compounds, sometimes they're ions and sometimes they're not. So we have to look at it as if it were a bookkeeping scheme, just to keep track of the electrons. It doesn't mean that, let's think of an example. How about this one? Methane. Methane is not an ionic compound, so we can't say that these are ions attached to one another. But we still use the oxidation reduction process, or oxidation state. And hydrogen is given a +1 charge all the time. Rarely is it a -1. And when it's a -1, well, you won't have to worry about that. I'm not going to throw that one at you in this class. But here we have a +1 for each one of those, so we have +4 total, right? So in order to make this whole thing neutral, carbon has to be -4, right? Now, carbon is not -4 charge in this compound because it's a covalent compound. They're just sharing electrons. They're not ions. But we use the same scheme as ions to keep track of our electrons. So if we did something to this and made a product out of it, then we could track whether the carbon had changed its oxidation state in the process. Okay, I just wanted to make that point so that you don't think that everything has to be an ion. These are only ions in that case, and sometimes we use this bookkeeping scheme for non-ions. Okay. Oh, these are some rules that we have to abide by. This is how you tell the difference. Oil rig. Oxidation is loss, reduction is gain of electrons. Okay. You didn't get a copy of everything, did you? Mm-hmm. Let's correct that deficiency right now. Thank you. Oh, before we get to that point, final exam. We need to decide if we're going to have it on a Tuesday, or if you need a couple extra days, we'll have it on a Thursday. The official schedule from the dean says Thursday, but it also says we start at 8 o'clock. I'd rather start at 9:30 as usual. But you can pick Tuesday or Thursday, and it depends on whether you need the extra days or whether there's a conflict with some other class. You might need to study for that class up to Tuesday and get that one out of the way, and then study for this one for Thursday. So just keep that in mind, and before we get to that point, we need, as a class, to decide how we want to do that. Okay. The oxidation state of a pure element is 0. Under standard temperature and pressure conditions, the oxidation state would be 0. So an example of that would be any of the metals would just be the symbol, like sodium. So its oxidation state would be 0. Okay. Some of them are diatomics, though, like hydrogen. That would be 0. And that's the oxidation state for each hydrogen in that molecule. Okay. Or chlorine, like we were doing before. Chlorine, 0. All elements under standard conditions are 0 oxidation state. Monatomic ions that I had on the board just a second ago. Each one of those ions, oxidation state is the charge on the ion. Okay. For oxygen, we take oxygen as -2. The only exception to that is when oxygen is part of a peroxide. And a peroxide is where 2 oxygens are bound together, and then they're bound to something else. So when you go to your medicine cabinet and you pull out the hydrogen peroxide, it's bound to hydrogens on either side. But that's only one type of peroxide. There are a whole host of peroxides, and we usually just say it could be anything, right? We use R because there's nothing up here but just R. R is just a placeholder. But anything bound to these. So both of them together are -2. So that means each one is -1. That's the only time oxygen is different. Okay. Hydrogen. Hydrogen in almost every situation is +1. Of course, if it's part of an acid, that's an easy one. It's always +1. It's only -1 in rare occasions, and I'm going to avoid those like the plague. Fluorine is always -1. The rest of the members of the halogens tend to be -1. Let's see. Let me flip this around a second. The halogens tend to be -1. But as you move down the family, you can have variations. -1 might be their first choice, but in some compounds, they could be other than -1. If they're part of an ionic compound, generally speaking, they are -1. But if they happen to be bound in a covalent compound where they're sharing electrons, they can be other than -1. So we're going to go through a procedure so that you can take the ones that are locked in to their oxidation state, do those first. Then you calculate the rest of them. And we'll work on that in just a few minutes. Okay. But fluorine is always -1. It never varies. If your compound is neutral, there's no charge, you don't have a polyatomic ion, for instance, then the sum of all the oxidation states has to be 0. Let's see, for instance, if we have let's take a simple hydrofluoric acid. Okay, we said that hydrogen's got to be +1, fluorine's got to be -1, so we add those together, that's 0. That's a really simple one. But if you had a more complex compound, they'd still have to add it to 0. And if you have subscripts, then you multiply those times the oxidation state first, then add them together. Right. So if we had something like, perchloric acid, this would be a -2, this would be a +1, this would be a -8 total, this would be a +1 total. So this would have to be a +7. See, in that case, chlorine is not -1. So we did the hydrogen and oxygen first because they're fixed, except for peroxides, but we don't have peroxide here. So then 4 times -2 is -8, and +1. So +1 and -8 is -7. That has to be balanced. Right, so then if we add those all together, they're equal to 0. Okay. More rules. Let's see if there are more rules. If the polyatomic ion, well, polyatomic ion will have a charge. So if there's a charge on the group, then the total of the oxidation states has to equal to the charge. And then there are the alkali metals, right? The alkali metals are going to always be +1 oxidation state. And the alkaline earths always +2. One that's not up there is these guys right here. Boron, aluminum, gallium, and indium. Maybe not indium, gallium. These three are +3. Right? That's not part of the rules, but it generally holds. So let's see if we can find the oxidation state of each of the elements in each of these compounds. Okay? So there we have K2Cr2O7. K2Cr2O7. And you'll recognize this part as a polyatomic ion. It's the dichromate ion. Remember at the very beginning of the semester when I said if you've got 3 or more elements in a compound and one of them is oxygen, suspect polyatomic. This one is a polyatomic. And the whole ion is 2-, so this is +1, so those balance. But we're looking at the oxidation states, so we're going to do them individually. This is an alkali metal, so it has to be 1+. Right? So 2 of those are 2+. Oxygen is always 2-, right? So that means 14- total. Okay? So 2 and 14, 2+ and 14- is 12-, right? So this is 12-. So that means these 2 chromiums have to balance those 12- with 12+. So that means each one of these chromium is 6+. Okay? And of course, it all adds up to 0. What if we're interested in carbonate ion? That's another polyatomic. The total has to be 2 minus, right? So the oxygen is 2 minus each, which means 6 minus total. But we have to hold out 2 minuses for that charge, don't we? So that means we only have to balance 4 minuses, which means carbon has to be 4 plus. And if we take the total of these oxygens at 6 minus and 4 plus for that one carbon, add them together, we get 2 minus. Okay? MnO2. Well, this should be fairly simple. Each oxygen is -2, so we have a -4 total for the oxygens. And we have 1 manganese, so the manganese has to be +4 to balance. How about PCl5? Okay, for this one, where do you start, right? Because we know the chlorine could be other than -1. But in this case, when you have a halogen with something else that's not a halogen, and there's not a rule already established for the elements, like for hydrogen, for oxygen, then you take the halogen at -1. Okay? So in this case, we start with -1 for that halogen, in preference to something for the phosphorus, because phosphorus could be almost anything. So this means 5 minuses for that chlorine. That means 5 pluses for that phosphorus. Okay? Oops. Well, this one should be easy because fluorine's always -1. So that means sulfur has to be +4 to balance those 4 fluorines. Turn this back around. Pick up the screen. There we go. Okay. So that was for individual compounds and determining oxidation states. Now let's see what's happened here. Oxidation states, all right, based on the rules, the elements are always 0 oxidation state. Right? So sodium is 0, chlorine is 0, and what will be the oxidation states for these? Well, we can start with sodium, since chlorine could be something different. Sodium's always +1, so that means chlorine has to be -1. No other choice. And in this case, sodium has lost electrons, so it's oxidized. And chlorine has gained electrons, so it's reduced. But we've introduced another term in this process. Whatever happens to be oxidized is the reducing agent. It's responsible for reducing chlorine. In this case, sodium has supplied electrons to chlorine, so it can be reduced. That makes sodium the reducing agent. And vice versa, chlorine is the oxidizing agent because it is responsible for accepting electrons from sodium. Okay. Now, here's one where we're reacting methane with oxygen. We're burning. It's like in one of our Bunsen burners. The natural gas and oxygen yield carbon dioxide and water. Okay? Believe it or not, this is an oxidation reduction reaction. And one way to tell without actually doing the calculations, anytime you have a combustion where oxygen is one of the reactants, it's an oxidation reduction reaction. Every time. But we want to do more with it. So, rather than just throw those up there, let's justify. With a marker that works. There's our methane. Here's our oxygen. And they've been kind enough to balance the equation for us. We're going to learn how to balance these things ourselves. But for now, we'll not look to give force in the mouth. Okay. So the oxidation state, we did this one before, where we're saying hydrogen's +1. That means 4 plus is for hydrogen. That means carbon has to be 4 minus. Okay. Oxygen is 0 because it's an element. On this side, oxygen is 2 minus times 2 is 4 minus. So this one is 4 plus. And in this case, oxygen, when you see an element by itself on one side and it ends up in a compound on the other side, then it has been either oxidized or reduced, one or the other. So we're going to focus on oxygen as the target of this change. So hydrogen is 1 plus each, which makes 2 plus here. That means oxygen has gone to 2 minus. Okay? Now that we have our oxidation states, we can decide which one's reduced and which one's oxidized. Carbon went from 4 minus to 4 plus. How did it do that? Gain or loss of electrons. If it's going from negative to positive, it had to lose electrons, didn't it? Okay. So we lost a certain number of electrons, but how many? 8. Right. It took 4 to get to 0, and then 4 more to get 4 plus. So we lost 8 electrons per carbon. And there's only 1 carbon, so that's the total. Then our oxygen went from 0 to 2 minus. So we had to gain. Anytime you have a loss, you've got to have a gain. Right? So here's the gain side. We gained so many electrons per oxygen. To go from 0 to 2 minus, we had to gain 2 electrons per oxygen. And we have 2 times 2 is 4. You know what? This is a case where oxygen ends up in 2 places. But it's gone to 2 minus in both places. So that makes our calculations easier. Sometimes one might go to 1, one might go to a different value. But in this case, 2 electrons per oxygen, and how many oxygen? Well, we got 4 here, and let's see, we got 2 plus 2 is 4 here. Okay, so times 4 was 8 electrons. So our electrons balance. Same number gained, same number lost. So that means oxidation is lost, so carbon is oxidized, and it also is the reducing agent. Oxygen is reduced, it's the oxidizing agent. Okay, now we get those. All right, this is sort of a recap. Redox reactions always transfer electrons. You can form ions by the transfer, but you don't have to. When we oxidize, the oxidation state increases. That is, it becomes more positive. So in this oxidation, we've become more positive to go from -4 to 4 plus. And reduction is a decrease in the oxidation state. It becomes more negative. So we go from 0 to 2-. Okay. Let's see if we can determine which one of these is an oxidation reduction reaction. And which is the oxidizing agent and which one's the reducing agent. All right, the trick I gave you earlier, if you start off with an element or you end up with an element, doesn't matter which, and it ends up in a compound, then you have an oxidation reduction. So we know this one's oxidation reduction without even calculating the values. But since we have to determine which is oxidizing agent and which one's reducing, we need to do that. So for this one, zinc and 2 hydrochloric acids yields that and that. I'll let that one do phases. And this one starts at 0. And this one is 1-, so 2- total. That means 2+ here. We went from 0 to 2+, which means what? Loss. We lost electrons, it's oxidized. That means it is the reducing agent. Because it's oxidized. So, which one was reduced? Well, as it turns out, this one's 0. This one's still 1-, but this one's 1+. So we went from hydrogen 1+, hydrogen 0, gained electrons. That means this is the oxidizing agent. Okay, there's our calculations. That is an oxidation reduction reaction. Let's see, is it going to give us? Yeah. That's the, in red, this is the reducing agent, color-coded. Kind of like the redacted documents. the Mueller report got redacted and color-coded so we know what happened to it. And the blue one is the oxidizing agent. Okay? How about the next one? This one's not so easy to tell. So we're going to have to say, all right, what's the oxidation state for each of the elements in this one? Okay, oxygen's 2-. That one's 2-, this one's 2-, that one's 2-. So that makes this hydrogen 1+. That hydrogen is 1+ because this one plus that one has to equal a minus. These have to add up to 0. So 2 pluses and a -2 is 0. Oxygen here is 2-. So this is 7 times 2 minus is 14-. And 2 chromiums balancing 14, actually 12-. Right, because we have to hold out 2 minuses. So each chromium is 6+ for this one. Okay, how about this one? Okay, this one's 4 times 2 minus is -8, but we only need 6 minuses to balance. So this one chromium has to be 6+. There's been no oxidation reduction in this reaction. The second one, oh, this is a neat one. 2 copper 1 chloride yields copper 2 chloride plus copper. Notice the copper ends up in two places. It ends up here, and it ends up here. This oxidation state 0. Since this one is a -1, 2 minus total, this one has to be a 2 plus. So copper has ended up at two different oxidation states from this origin, which is 1 minus, 1 plus. So one of these coppers, there are two of them, one of these coppers was oxidized, means it's a reducing agent, and the other copper went to here. It was reduced. This is called a disproportion H reaction. When you end up in two different places at two different oxidation states. If they end up at the same oxidation state, then it's not disproportionation. Okay, so there we go. One of these is the reducing agent, and the other one is the oxidizing agent. Okay, now we're going to learn how to balance equations using what we've learned about oxidation reduction. Some reactions, in fact, most reactions, can eventually be balanced with our original techniques. Where you just use that budgeting model where you put your elements down one side and you total them up and make your changes to the coefficients. But some of them are what we call recalcitrant. They will not balance unless you use a redox method. This is called method of half reactions. So basically what you do is you take the reaction that's given to you, that's unbalanced, and you split it into two reactions, one oxidation, one reduction, and you balance them separately. Then you bring them back together for your final balanced equation. Okay? So let's see, what are we doing here? Well, this is a balanced equation. And if we check out which one's which, we determine all the oxidation states for our elements or ions. Then the reduction side is this one, where the manganese has been reduced from +7 to +2. And the oxidation side is iron 2 plus going to iron 3 plus. But now let's do one ourselves. Right? These are the rules for acidic solution. That's your starting point. You always assume that the solution is acidic. If the solution happens to be basic, you still do the acidic balance. And then after you've done that, you change it to basic. We'll do one of those two. But the acidic is the one you need to master. And these are the steps you go through. You split the equation into two half reactions, one oxidation, one reduction, with just what you have, what you're given. Then you start to balance it. First, you balance all the elements that are not hydrogen and oxygen. The reason for that is we're going to insert protons and water molecules to balance the hydrogens and oxygens. So first, you balance everything but those. Then we go in and balance the oxygens using water. And then we've added hydrogens in the process, so we balance the hydrogens that we added with protons. Then you balance the electrons after you've reached that point. Then you add electrons on whichever side is appropriate for oxidation or reduction. Then when you bring the equations back together, you might not have the same number of electrons in the oxidation as the reduction. So you multiply one or both of them by some value so that you end up with the same number of electrons transferred in each half reaction. Then you can add them back together. So let's take an example. Let's see. I'm going to put that one over here. I'm going to take the dichromate ion. And like I said before, there are spectator ions that are associated with these. We just leave them out because we don't need them. Right? The dichromate ion might be introduced into solution as a potassium dichromate. That would be soluble. And the sulfite ion might be introduced as, say, a sodium sulfite. But the potassium and the sodium don't matter. They're not going to change anyway, so we just leave them out. Then we have the sulfite. And then the products are the chromium 3+ ion and the sulfate ion. Okay. First thing we have to do is decide which one's oxidized, which one's reduced. So we take our oxygen at 2 minus times 7 is 14 minus. We have to hold 2 minuses out for the charge. That means the chromium has to balance with 12 pluses, and each chromium then must be 6 plus. Then this oxygen is also 2 minus, which means 6 minus total charge. We have to hold 2 minuses out for the charge. That means this sulfur has to be 4 plus. This chromium is its charge. That's easy. This one is 8 minus to begin with from the oxygen, but we're going to hold out 2 minuses for the charge. That means this sulfur is 6 plus. Okay? Now that we know what our oxidation states are, we can set up our separate half reactions. So, oxidation. Which one lost electrons? That one didn't it? Went from 4 plus to 6 plus, it lost 2 electrons. Okay. So we write the SO3, 2 minus, and give ourselves plenty of room because we're going to be adding things in there. And then it goes to this one. In reduction, we'll move down here a little bit because we may have to modify the equations. So we give ourselves plenty of room. If that's the oxidation, then this one has to be the reduction. 6 plus, this is 4 plus. And that one's going to 3 plus. 6 plus. Okay, now we have our half reactions. Next step, balance everything that's not hydrogen and oxygen. 1 sulfur, that's good. 2 chromium, 1 chromium. So we need 2 chromiums there. Next thing, oxygens. We've got 3 oxygen here, 4 oxygens there. So we need an extra oxygen over here to balance. Okay, there's our extra oxygen. 3, 4. On this side, we have 7 oxygens and none over there. So we need 7 oxygens over here as water. Okay? Now we balance the hydrogens that we threw in there. We put 2 hydrogens in here, that means we have to have 2 hydrogens over here. And since it's acidic solution, our hydrogens are protons. On this one, we've got 14 hydrogens over there. So we need 14 hydrogens over here. Okay? Now we need to do electrons. This one lost 2 electrons. So when you lose 2 electrons, they end up on the product side, right? They were buried in here to begin with. Now they're extracted out over here. 2 electrons from each sulfur, so we only need 2 of them. And we do it on time. Okay. I don't know if we're going to make it through today. We might. Think positive. Okay. For this one, we've gone from 6 plus to 3 plus. Right? So for each chromium, we had to gain 3 electrons, right? We gain 3 electrons for each chromium, but how many chromiums do we have? We have 2. So we actually gain 6 electrons. Right? Gain 3 for each chromium, 3 for each chromium, but there's 2 of them. So we need 6 electrons. Now we need to, I know what you're thinking. You don't gain 6 electrons by putting them over there. Right? I put them on the wrong side. To gain 6 electrons, they have to be here, added together. Then they end up over here. Okay, now that the electrons are on the right side of the arrow, we need to balance the electrons. All we need to do is multiply this one times 3. And that will give us the correct number of electrons on the product side. Okay, so we have 3 SO3 2 minus plus 3 water yields 3 sulfates. 3 times 2 is 6 hydrogens, and 3 times 2 is 6 electrons. Okay? Now we're going to add this one to this one. And we've already set the equations up so that the electrons balance, right? So the electrons cancel. We don't even have to bring those down. But we can bring everything else down. So we're going to have 1 dichromate and then 3 sulfites. Okay, then we're going to have 3 waters and 14 protons. Okay, that's the reactant side. The product side, we're going to have 2 chromium 3 plus ions and 3 sulfates. Then we'll have 7 water and 6 hydrogens. Okay? Let's see, that was 1, 2, 3, 4, 4. 1, 2, 3, 4. 4. On this side we had 1, 2, 3, 4. 1, 2, 3, 4. Now we just cancel things that are common to both sides. Right? So we have 3 waters here and 7 waters there. So these 3 go out, and that leaves us with 4. Okay? This side we have 14 hydrogens, that one's at 6. So all of those go out, and that leaves us with 8 on this side. Okay? So that's our balanced equation. Let's see, there's our reduction equation. This is our oxidation equation. Then we had to multiply, let's see, there's more to it. Those are steps that have already been done. Add them together. There we go. Cancel commons. Combine the equations. And there's our balanced equation. So 8 hydrogens, 1 dichromate, 3 sulfites, and 4 waters, 2 chromium 3 plus, and 3 sulfates. Okay? Any questions? Okay. This takes practice. You have to be very methodical about it. Follow the steps. From beginning to end. And you shall be rewarded. I'll watch Harry Potter this weekend. All right, we could do this one. But I want to get on to, let's see, this one's the acidic solution. Okay. We can do this one because I'm going to use this one. We're going to do this one in acidic solution, and then I'm going to show you how to change it to basic solution. So we'll start with this one, acidic. So we're starting with bromine ion and the manganate ion yields bromine and manganese 2 plus. Okay? So this one's 0, that one's 2 plus, this one's 1 minus, and this one we have to calculate. So 4 times 2 minus, right, is 8 minus, but we hold 1 out. Right? So this one has to be 7 plus. And we check ourselves. 7 plus and 8 minus is 1 minus. So now we can write out our oxidation reduction equation. So the oxidation equation is the one where we're going to lose electrons. So bromine went from 1 minus to 0. Each bromine had to lose 1 electron. So that means Br minus yields Br2 at 0, and that's a minus. And the reduction, manganese went from 7 plus to 2 plus, so it had to gain 5 electrons for each manganese. NO4 minus 7 plus for that one. And this manganese is 2 plus. Okay? So, 1 bromine here, 2 there. So we need 2 here. 1 manganese there, 1 manganese there. We're good. Now do oxygens. No oxygens up here. We have to deal with them. Oxygen there, so we need 4 oxygens. So we need 4 waters, 1 each. Now for hydrogens, right? We added 8 hydrogens over there, so we need 8 protons over here. Now we do electrons. If this is oxidation, we've lost 2 electrons. That means the 2 electrons have to be over here. 1 electron for each bromine, we've got 2. So this side, we have to gain electrons. So from 7 plus to 2 plus, we had to gain 5 electrons. Now we need to match up our electrons. So we've got an even and an odd. That usually means cross multiply. So if we take 2 times this one and 5 times that one, we should end up with 10 electrons in each equation. So this one will give us 10 bromide ions, yields 5 here and 10 here. Okay, so we're going to take that one and add it to this one. So we have 2 there, 16 here, 10 electrons here to match those 10. And then we have 2 of these, and 8 of those. Okay? Now, 10 electrons over there, 10 over here, cancel. And then we can add them together because there are no hydrogens up here to cancel. There are no waters up here to cancel. So now we just add them together. So we've got 2 manganate ions plus 10 bromide ions plus 16 protons. 1, 2, 3. 1, 2, 3. And then here we have 2 manganese ions plus 5 bromine molecules and 8 waters. Okay, so that's our balanced equation in acidic solution for this reaction. And that's step by step. I like to do it on the board like this because my students tend to follow it better than follow those moving items in the slides. Now let's see, we need a final balanced equation to see if it matches. Two manganates. Oh, I haven't canceled everything yet. There we go, cancel the electrons. 16 hydrogens. Oh, we have to add them together, sorry. There we go. 2 manganates. 10 bromine, 10 bromides, 16 hydrogens, 2, 5, and 8. So we're good there. So this is our balanced equation in acidic solution. Okay? Now, what if this reaction took place in basic solution? How do you deal with that? Once you get to acidic solution, it's balanced. So I'm going to erase all this other stuff and work with the balanced acidic equation to show you how to change it to a basic equation. Okay. There's our balanced one. So what we need to do to change it to a basic solution is get rid of all those hydrogens, all these protons. And you do that by reacting them with hydroxyls. Okay? So if we add 16 hydroxyls here, we have to do that same thing to the other side. Right? So we have to add 16 hydroxyls over here. All right? So what do these hydroxyls become? Remember, the net ionic equation for an acid-base reaction is protons plus hydroxyls yields water. So this makes 16 waters. Okay? Now you cancel waters because you've got 8 waters over here, 16 over here. These are gone, and these become 8. So the balanced equation, which I didn't put up there because I just created this slide, is 2 manganetes plus 10 bromides plus 8 waters yields 2 manganese 2+ ions plus 5 bromine molecules plus 16 hydroxyls. That's basic solution. This is what I call my fake acid method. You do the acid first, then you convert it to hydroxyl. To hydroxyls, which is basic solution. Okay? Oh, good. We got time. We'll jump into. All right, that was redox reactions. And the logical progression from there is to derive some energy from these reactions. I mean, that's usually what we're after. Products could be energy. Products could use energy. And in order to do that, we need to know where's the energy going and what form is it taking. Right? In redox reactions, the energy is being transferred by electrons. So electrons are going from a higher energy state to a lower energy state. And in the process, we want to extract that energy. Right? You could mix all these things together and the reactions will go, but you wouldn't have access to the energy because you can't get to the electrons. We need to find a way to get at the electrons so that we can harness that electrical energy that's taking place when the chemical reaction occurs. That's electrochemistry. It's an interchange of chemical and electrical energy. So how do we do that? Well, you can produce an electric current from a chemical reaction. We generally call that a battery. The chemical term for it is a galvanic cell. Or you can use electricity to make the reaction go backwards. Right? If the reaction is spontaneous, we're going to get energy from it in the form of an electric current. But if we want the spontaneous reaction to run in reverse, we have to supply an electric current with a high enough voltage to push the reaction backwards. That's called electrolysis. So, one or the other. The electrochemical cell, or the galvanic cell, is a combination of 2 half cells. We've already split our reaction into half cells in order to balance it. Now we're going to take each one of those half cells and physically separate them. And then we will connect them through a wire, and that gives us access to the electrons as they move from one to the other. So in this case, we have these two half reactions, right? This one is going to be from 2+ to 3+, so it's oxidized. That means this one has to be the reduction side. Oxidation reduction. So we separate those into two separate physical containers, and we connect them by a wire. On this side, we have Fe2+ is going to be oxidized to Fe3+. That's 1/2 cell. On this side, MnO4 is going to be reduced from, let's see, 7+ to 2+. So it's going to be reduced on this side. And since the reduction is taking place on this side, the electrons are flowing this way because you need electrons to come out over here in order to do that reduction. Okay. Okay. This reaction is not going to go yet, because in order for those electrons to move through this wire, they would have to build up an excess negative charge on that side and a positive charge on this side. So we borrow from physics, and physics says that you don't get electron flow unless you have a circuit. That is, you have a complete pathway from one point all the way around back to that same point for the flow of electrons. So what we need is a way to connect these two together. You could do it with a porous disc in between, because you don't want the solutions to mix. If you let them mix, then you've lost your advantage, right? But you do want to provide a pathway for the exchange of ions so that the charges can balance. So one way to do that is with a salt bridge, right? So we just put a plug in the end of this bridge and we fill it with a salt solution so that it'll conduct current and transfer cations and anions backwards and forwards to balance the charge. Or we can use a porous disc like this. This is more efficient, the porous disc, but you have to construct your glassware to handle that. It's easier, particularly in a laboratory setting for students, to just make a salt bridge. And my general chemistry class is going to do that next week. We always, the last thing of the year we do for my Gen Chem 2 class is make a battery. Okay, so now we have a circuit. Electrons flowing this way and counter ions flowing back that way. We have a complete current going through. And we can measure it. All we have to do is stick a meter right here in line with that, a voltmeter, right? And you can tell what the voltage is for that chemical reaction. Okay. So, more terms. The side that at which oxidation occurs, now remember we've separated these two half reactions. So one side is oxidizing, the other side is reducing. The one where the oxidation occurs is called the anode, right? So in that case, the electrons will leave that solution through the wire, because we're extracting electrons from that side. That's the oxidation side. Going through the wire to the other side where the reduction takes place. And on the reduction side, that's called the cathode. Okay? How do you identify the difference? I always look at it this way. The cathode side is the side where the cations move toward the electrode because it's sending electrons out that electrode. Well, the negatives are going to attract the positives, right? So on the cathode side, and we call positive ions cations, so the cations and the cathode move toward the electrode to be reduced. Okay, the other process, electrolysis, is just the battery in reverse. And every time you start up your car, you're using your battery as a galvanic cell. You're extracting energy from it to turn the starter motor and rotate the engine. And that draws energy out of the battery and partially discharges it. So you want to put that energy back. Well, in order to do that, you've got to, the spontaneous reaction gives you energy to start your car. But once you get it started, then the gasoline combustion turns over your alternator and you send direct current back through the battery in the reverse direction. And that's the electrolysis. The reaction that you're driving is non-spontaneous. You're driving the spontaneous reaction in reverse to recharge your battery. You always need, it has to be non-spontaneous, you always need an external source of electrical energy to drive that reaction in reverse. One example that we don't see much anymore except on antique cars is chrome plating a bumper. Right? You take a steel bumper, can't put chrome directly on steel, it won't hold, it'll flake off. So first thing you have to do is do the electrolysis with copper. And sometimes they use nickel because they bind better with the iron atoms in the bumper. So once you've formed that layer, then the chrome sticks to nickel and copper very easily. Then you can put your chromium layer over the top of that. But you just stick that bumper in your solution of chromium and you run a charge through it. That becomes the cathode. The bumper is the cathode. Electrons are coming out from there. The chromium ions are being reduced to metal, right? They're going from a plus charge to 0, and they plate on the bumper. This is a reaction that takes place in your lead acid battery under the hood of your car. All right, this is the anode. So the lead is being oxidized to lead 2+. It went from 0 to 2+, okay, and gave up 2 electrons. The reduction side is, this is one plate in your battery. The counterplate, the other plate in the battery is lead 4 oxide. And it's being reduced by those 2 electrons to lead 2+ sulfate. So the product is the same on both sides. The lead sulfate sticks to the plates. And then when you run a charge backwards, it runs this backwards, produces that, runs this one backwards, produces that, and reconstitutes your lead oxide plates in your battery. Okay? The nice thing about this is, notice that the solution that they're immersed in is sulfuric acid, right? So you don't need a salt bridge. You can stick both those plates in the same solution and you can eliminate the added complexity of a salt bridge or a porous plate or whatever you need to separate the reaction mixtures. That's the nice thing. One of the nice things about a lead acid battery, right? It makes it more compact, even though it's heavy as hell. But, and then the other thing is, it produces a very high voltage. for each cell, you get 2 volts. So that's why most batteries for cars are 6 cells in series. So when you put 6 cells in series, you add up to 2 volts. That's why your battery is 12-volt battery. You put those 6 cells in series. I think some trucks and tractors might have 24 volts. I've even heard of 48-volt batteries.
I know boat batteries are big.
For what?
Boats.
Boat batteries, yeah, okay. Do they have a higher voltage, or are they just bigger batteries?
They're bigger batteries. I'm not sure about the voltage.
Yeah, they could have the same voltage, but have bigger cells.
Yeah.
The bigger cells means that they run longer before they completely discharge. Oh, the other item, you know, as your plates are coated in this lead sulfate and you recharge them, you never reconvert everything back to its original constitution. You always leave a little bit of sulfate behind.
So boat battery is 12.7 to 12.8 volts. So
okay. Yeah, this is an average, 2 volts. You can get more volts out of it with your battery design. But over hundreds of cycles of charge and recharge, you gradually build up a layer of lead sulfate, which occludes the underlying metal or oxide from the solution on the outside. So the reaction cannot occur anymore. At that point, your battery is dead and cannot be recharged. It's called, they say it's sulfated out. In that case, you have to recycle it. Just get a new one. I think the one in my van is getting close to that. And that's when they test the battery, they're looking for the amount of current that it can supply. And that current supply is an indicator of how much sulfate has built up on the plates. You know, it might be rated at what, 700 amps. Some of them are that big, some of them are 450s, 500s. But it starts to drop over time. Okay. It used to be what they would do is they would stick this hydrometer down in your cell and pull up some of the solution and read the density of the sulfuric acid. And as you use the battery, the sulfuric acid is consumed and not replaced. And the density is an indicator of what the concentration is. And once you reach a certain point, you can either replace the battery. What they usually do is the technician would add a little more sulfuric acid to it and see if that restored it. But now, most of our batteries are sealed. You know, all they have is little tiny vent holes for, if you overcharge the battery, you get hydrogen gas. And if you don't let it vent, you know, you have potential for explosion. Okay.
on their lab when they exploded, somebody set a fire down in their bottom and threw a couple batteries in there, and when they exploded, it busted the windows out of the houses nearby. And it was bad.
Where was this?
In their bottom, where I live at, down in their community. They threw 2 batteries in the fire, and when they finally exploded, the nearby houses around it blew the windows out.
Oh.
Yeah, the concussion.
Probably had a bonfire.
Yeah. Yeah, and somebody had the right idea with their batteries on it. It's bad.
Well, you know.
Yeah.
There's no explanation for stupidity, is there?
No.
It just is.
Yeah.
Okay, so we mentioned voltage. Voltage is like pressure in a water hose. The higher the pressure, the higher the voltage. There's a bigger push behind those electrons to go from one place, from one cell to the other half cell. So the higher the voltage, the bigger the push. And to get a relative idea, you're a guy, I'm a guy. All little boys take a 9-volt battery and stick it on your tongue, right? Just to see, and there's a tingle.
Yeah.
But 9 volts is no big deal, right?
Yeah.
But if you go up higher voltage, like stick your finger in a socket, that's 110, 115, sometimes 120 volts. You'll feel that one. So the higher the voltage, the more likely you are to get conduction through your body. So this pressure is measured in volts. Its electrical potential is another word for it. If you put those cells in series, you add up the voltage. If you put them in parallel, you just put batteries side by side and just connect the positive terminals all the way down this side and the positive all the way down that side. You only get the voltage of that battery, of individual batteries. But it'll last longer. But if you put them in series, like go positive, negative, positive, negative, positive, negative, all the way down, add up the voltage of each of the batteries. Say if you put 4 12-volt batteries in series, you get 48 volt total. Yeah. So there's a bigger push if you put them in series. Yeah. Dry cell batteries, like kind you put in your flashlight. They're different versions. They're called dry cells because they don't have spilling liquids like you would have in a lead acid battery. But you still have an aqueous environment within the battery. It's just kind of pasty. There's not a lot of water. So they call them dry cells because you can't spill them. They're sealed. And most of them are not rechargeable. They do make dry cells that are rechargeable. But I've used that system and they're good for maybe 50 recharges and then they, so they're hardly worth it. Okay, so we're not going to mess with those. Dry cell batteries, let's see, other types, okay. Silver cells, those types of batteries, usually you'll see those in calculator batteries or hearing aid batteries. The mercury cells are not used anymore for obvious reasons. I mean, that's a serious contaminant. Nickel cadmium, you remember nickel cadmium batteries? No, they used to use NiCad batteries in things like my rechargeable trimmer that I use for all my beard. I've had that thing for about 20 years. It's still working. The problem with nickel cadmium batteries is they have a memory. So if you partially discharge it and then recharge it, it thinks that its 0 point is where you left off when you recharged it. Yeah. So it'll discharge there and stop. So what you do is periodically, I take I just set it in the stand, turn it on and let it run until it's just dead, completely dead. Then recharge it and it has its full capacity again. But now it's more common to see lithium-ion batteries. They're lighter. Lithium is a lighter metal, so that stands to reason. You know, it's over here. And they have a higher charge density than other batteries. That is, for the same volume of battery, you get more charge out of it. Okay, so that's good. And that's why they use them on electric cars. Right. Before that, lead acid batteries, they tried electric cars before with lead acid batteries, but the weight was too much. I mean, they would provide all the power you need to turn the wheels, but you got to get all that mass moving. So lithium-ion batteries were more efficient. The problem with lithium-ion batteries is they have a tendency to overcharge. So they have an electronic circuit in each battery that says, okay, when it gets to 100%, cut it off, no more charging. Because if you overcharge it, those are the ones that tend to explode. Corrosion. Corrosion is another word for converting a metal into something else, undesirable, usually the oxide of the metal. So if you bury an iron pipe in the ground, eventually it's going to turn into rust. Right? So one way to circumvent that is connect a more active metal to the iron pipe and sacrifice that metal. Magnesium is more active, so it will corrode. And as it does, it provides electrons from that corrosion through the wire to the iron pipe. And the iron pipe then becomes the cathode, and it preserves the metal in its reduced form, whereas the magnesium is gradually eaten away. Ocean-going vessels use cathodic protection. That's what this is called. It's got the name. Yeah. They use cathodic protection. They'll wrap the hull below the waterline in a belt of zinc. And if there's no power in the ship, the zinc will do the same thing. It'll corrode and supply electrons to the iron hull and keep it from rusting. But as long as there's power in the ship, they trickle a direct current of electrons into that zinc, and that keeps the zinc from corroding too. So the only time the zinc is actually used is when power's off on the ship. And then the corrosion. And if the zinc oxide doesn't flake off, then when they supply that trickle charge, it reconverts that zinc oxide to zinc. Now, barnacles, that's another story. They're living systems. You can't. I could imagine you could send a periodic shock through the hull, keep the barnacles from attaching. I'm sure that's been tried. Okay. Electrolysis. The term, let's see. One second. This is one form of electrolysis that's very useful. You can take water, run a direct current through it, and split it into hydrogen and oxygen gases. I used to have a device. Oh, I'm out of time. I won't tell you. The demonstration, they used to show the class. Electrolyze water and catch it in the tube up here. Catch the hydrogen, get a burning ember and go pop. Just to prove that I had done that.
Yeah.
But this is part of the holy grail of energy production and storage. If you can split water into hydrogen and oxygen, hydrogen is the fuel, oxygen you can let it go in the atmosphere, and then when you burn the hydrogen or run it through a fuel cell to get electricity out of it, the byproduct is water. That's it. No carbon dioxide, just pure energy, and water is a byproduct. There are certain problems with fuel cells, one of which is temperature. You have to run the thing so hot.
Yeah.
And the other thing is storing hydrogen in your vehicle. If you want to run 400 or 500 miles, you need to store it. And there are no good answers yet. Okay, that's it. And I'll shut this down, convert it, and post it by the end of the day.